Where on the linear demand curve do we maximize revenue? We have seen that at the midpoint of the linear demand curve, revenue is maximized. The examples that we use include the demand curves for business and tourists given as follows. QB equals 330 minus PB, and QT equals 250 minus PT. Again, we have determined that at the midpoint, i.e. a price of $165 for business and $125 for tourists, the maximum revenue in each market segment would be obtained. This is price discrimination, charging different prices to different customers. The revenue at price equals 165 and a quantity equals 165 is 165 squared. The revenue at price equals 125 and quantity equals 125 is 125 squared. We can show that if the price were a little higher or a little lower, the revenue would be lower. We try for price equals 164 and a quantity of 166, and then we flip that to a price of 166 and a quantity of 164. Notice this is the same arithmetic problem, and we will show that the revenue will be lower than at the midpoint of the linear demand curve. Similarly for P and Q equals 125 on the right hand side. We conclude that revenue is maximized at the midpoint of a linear demand curve. 165 squared plus 125 squared gives us a revenue of $42,850, and we can show that this revenue is higher than if we charged a single price. In order to charge a single price, we need to aggregate the demand across the two market segments, and we get Q equals 580 minus 2P because PB is equal to PT. At the midpoint of this linear demand curve, we will have P equals 145 and Q equals 290. And we can show that this revenue will be $42,050, which is $800 less than if we were to price discriminate and charge a price of $125 to tourists and $165 to business passengers. We conclude that charging different prices to the 290 passengers by type will lead to higher revenues. We will now show that if we wanted to maximize profit, we would raise the price in each market segment, and by equating the marginal revenue in each market segment with the marginal cost, we would alter the quantity of passengers. So we're going to have 270 passengers at a marginal cost of 20, and we will allocate these passengers 115 as tourists and 155 as business passengers. With the allocation of the passengers, 155 business passengers and 115 tourists, we can determine that the prices in the market segments would rise to PB equals 175 and PT equals 135. We show the equilibrium in each market segment at a price of 175 and quantity of 155 for business, and in the tourist market segment a price of 135 and a quantity of 115. We can determine that the profit would indeed be maximum in this particular situation. Notice that because the cost of servicing each passenger is 20, we know that there are 270 passengers, so our cost is effectively fixed if we fill 270 seats at $20 each. And then the second fixed cost would be the cost of leasing the aircraft. Just taking a look at this particular setup, if the cost the variable cost is going to be effectively fixed, and the lease cost is also going to be fixed, then maximizing profit is effectively maximizing revenue subject to seating 270 passengers. Hopefully that makes sense. A moment ago I said that maximizing profit when all of the passengers are being charged the same amount is tantamount to maximizing revenue subject to the constraint of filling a certain number of seats. The quantities and prices will be the same, and the profit will be the same. Here's a setup for the revenue problem. Maximize R equals RB plus RT subject to QB plus QT equals 270. Once we plug in the inverse demand equations, we get the revenue functions subject to the constraint. I have mentioned several methods for solving this problem. The most straightforward might be the substitution method, in which case you take the equation, that is the constraint, and rewrite it in terms of one variable, and then you substitute that into the second variable so that we can have a simple two-dimensional function, revenue a function of either QB or QT. It makes the differentiating straightforward. After manipulations, our revenue function becomes R equals 620 QB minus 2 QB squared minus 5400. When we differentiate that function, we get dr dqb equals 620 minus 4qb, set equals 0 to get the maximum on the revenue function, which we see is quadratic with a maximum or a peak because of the minus 2 on the q squared term. QB equals 155. You plug that back into the demand equation. PB equals 175. Now that we know QB, we can plug that back into the constraint. QT equals 270 minus QB, and we get QT equals 115. Plug 115 back into the demand equation for tourists. PT equals 250 minus 115 equals 135.